Hello everyone, my name is David Tran, and today I'll be talking about computational fluid dynamic analysis and design optimization of jet pumps. Introduction. Supersonic jet pumps were developed in the 19th century, and pictured on the right, this is how they typically look with the high velocity jet entering the entrainment zone. You have the throat in the middle and the diffuser towards the end. And the reason why these jet pumps were researched is due to them being a environmentally friendly component in areas such as refrigeration and air conditioning systems. And typically these are used in single and two phase flows, thermal power plants, and refrigeration systems. Analysis and results. This academic paper deals with the analysis and design of supersonic gas flows in jet pumps, and through high fidelity CFD analysis and experimentation through a formal optimism framework, they're trying to improve the jet pump efficiency. And during their CFD analysis, they use good grid resolution and the termless model standard K epsilon. The reasoning behind using standard K epsilon is that there is a 10% reduction in computational costs and there is no loss in accuracy compared to other turbulence models. So initially what they did is they set up a baseline jet pump design pictured over here on the right. And using the equation shown below right here, which is the momentum change through the diffuser, the reasoning behind this is that this allows the design to not have thermodynamic shocks occur. And the conditions at the inlet were to be uniform static pressure. The reasoning behind this is to avoid things such as high pressure gradients and reduce pressure losses. And once this thing was set up, they were allowed to calculate things such as pressure, temperature, and Mach numbers based on the design shown. This graph shows the Mach number distribution within the jet pump, and when comparing the CFD study numbers and the analytical calculations shown, they vary significantly. The reasoning behind this is that at first they thought it was due to the one-dimensional nature of the analytical method, where it is assumed that the flow entering the diffuser has a uniform Mach number. However, that proved not to be the case. This picture shows that the flow entering the diffuser consists of a central supersonic jet surrounded by low entrained flow, meaning that the effects of thermodynamic shocks are not captured within the analytical framework. So after that was done, they used the same initial baseline jet pump design and they parameterized it using this equation, which R being the diffuser radius, A2 and A3 being the diffuser shape, and A1 and A4 being the inlet and outlet radii. And this was used to identify design variables that has the greatest influence on pump performance. So once the calculations were done, they determined that the inlet radius of the diffuser and the nozzle radius offered up to 300% improvement in vacuum pressure, while the length of the diffuser and nozzle didn't really affect the pump performance at all. However, when you decrease the diffuser radius or increase the nozzle radius, it causes the efficiency to drop. The reasoning behind this is that increasing or decreasing both of those parameters will cause the pump to stall as the flow enters the diffuser. And the diffuser accelerates the flow, which leads to a sudden drop in efficiency. And pictured on the right shown is a graph that shows the influence of the diffuser inlet radius on vacuum pressure. So once they figured out what design parameters actually affect the pump performance, a optimization study was conducted. So they created a surrogate modeling approach, which essentially a surrogate model is an engineering method used when an outcome of interest cannot be easily directly measured. So a model of the outcome is used instead. After that, they used a optimal Latin hypercube method for the design of experiments, and the multi-objective permutation genetic algorithm was used to have uniformity in these points and in order for the validation and the combined DOE points to be optimized. So essentially, they did 70 build points and 30 validation points, where they took a boundary condition of 200 liters per minute. And the results are shown on the right. So once all the design points were calculated and the results were shown on the graph, they used genetic algorithm and sequential quadratic programming. And what happened was that the GA and the SQP were repeated on the surrogate model until a desirable design was found. So the first approach used was a MOS approach, and the second approach was a high closeness of fit approach. And this was repeated again and again until the GA produced a design which reduced boost air usage, resulting in a 21% reduction of power requirements. And the table shows the design process after each programming or algorithm outputted a design and the different results that the design would output. So once the GA was able to produce a optimal design, it was compared with the surrogate model. And when compared to the model, it was in pretty good agreement. It showed that it had a vacuum pressure of 12.9 kPa and it gave a primary air usage of 6.49 times 10 to the negative fourth meters cubed over seconds. And it gave an efficiency of almost 33%. And the graph on the right shows a comparison between the models and their efficiency over a range of entrained flow rates. So in conclusion, the academic paper was able to provide substantial improvements to the jet pump performance through high fidelity CFD analysis agreeing with the experimental data. And overall, this paper proved that they were able to reduce the pump power requirements by over 20% and increase the pump efficiency by 29% to 33%. Thanks for watching. Have a great day.